Here is a common example of a condensation-elimination reaction. As you can see, there are two monomers coming together to form a polymer. This polymer happens to be nylon, which is a common synthetic plastic. So here, one of the monomers is adipic acid and the other is hexamethylene diamine. And in red here, we have an OH from one of the monomers and a hydrogen from the other monomer. And when you combine these two monomers, the OH and the H combine and they form H2O, which is over here, as one of the products. The rest of the monomers combine to form nylon, the polymer. And that is an example of a condensation-elimination reaction. Here's the structure of our first common synthetic polymer, polyethylene terephthalate, or PET. This polymer is commonly used in food packaging, overhead projector films, aluminum-coated reflective material, and much more. Now, this structure is responsible for many of the properties of PET. Specifically, this aromatic ring, right here, gives PET a notable amount of stiffness and strength. Also, just a fun fact, PET is the most recycled plastic. Here is the structure of our next common synthetic polymer, nylon. This structure was used earlier to explain condensation-elimination reactions. And in this structure, there is a peptide bond that forms right here. And this peptide bond is actually responsible for many of nylon's unique properties. Additionally, this hydrogen right here that is bonded to an electronegative nitrogen is able to do hydrogen bonding, which is very unique to nylon. And this results in properties such as toughness, stiffness, and resistance to fatigue and temperature. Therefore, nylon is one of the most versatile plastics used today. Here's the structure of our third common synthetic polymer, polyethylene. Polyethylene is the most widely used plastic in the world. It is commonly used in plastic bags, milk jugs, garbage containers, and much more. Now here I have the branched version of polyethylene, which is known as linear low-density polyethylene, or LLDPE. Now, as you can see, there are obviously branches coming up from both of the CHs. And what makes the branched version so special is that these branches inhibit close packing, and therefore this version has a very low density. Last but not least, here's the structure of polypropylene. Polypropylene is commonly used in binder covers, plastic bottles, and more. Polypropylene has this additional CH3 group, or methyl group, right here. And this CH3 group is responsible for improving mechanical properties of polypropylene.